as we have already discussed few things regarding the artificial neural network, here we will start with a specific type of artificial neural network that we call single layer perceptron. By definition, in machine learning, a perceptron is a simple model of biological neuron in a artificial neural network. Now, why it is called single layer perceptron? Single layer means what? Coming to very soon. But before that, remember this single layer perceptron is actually the first ever model created. Okay. And the single layer means actually you have only one input layer followed by an output layer. There is nothing in between that. Single also you can say that where I have two layers, inputs and outputs, but it's not like inputs and outputs are not considered as a two different layers here. Single layer means actually there is no other layer present in between input and output. That's why single layer. Directly they are connected. Now here it is saying that we have written a point, very important point actually, which we will understand it more. That is, single layer perceptron is only capable of learning linearly separable patterns. What is linearly separable patterns? We will understand it, but before that, let's try to understand how we can utilize this single layer perceptron for solving a problem which is linearly separable. That means you can simply draw a straight line between two set of data sets to classify in as 100% accuracy. So just assume a scenario like this. We have a data set here, as I have represented here, a very small data set having two different classes of fruits. Okay, and the features by which we are creating the classes based on weight and length. So you have two features. Okay, for every class I have two samples. So just for reference, I have drawn a diagram here, a graph here, where I have two axes representing the two features. X1 maybe its weight and x2 is the length. And if I just try to put their based on their value, if I put the pattern in the if I draw the pattern on this plane, it looks something like this. This is in one side, this is in the other side. So you can simply you can easily draw a straight line, which basically classifying these two fruits, I mean these four fruits into two different classes with 100% accuracy. And that is my task, that train a single layer perceptron model using the above parameters to classify the two fruits. Okay, and once it will be trained, then I will get a new data. Okay, I will get a new data, say a unknown fruit whose class I don't know, but obviously I have the features of the fruit is available. That is, the weight of the unknown fruit is 140 grams and the length is you know uh, 17.9 centimeters. So I'm sorry, it's not 17.9, it may be 0.179 or something like that, whatever. And weight is 140 gram, means basically 0.14. I mean, yeah, 0.14 gram, yeah. Right. So anyway, so we have to find out the which class this unknown fruit belong. But before that, we have to teach the model so that it can create this classification boundary properly. Right. So let's do one thing. First, understand the set of steps that we will follow, and then what we can do, we can simply try to show you what I will show you, that by taking one pattern at a time. This is one pattern, right? This is one pattern, this is another pattern. So taking one pattern at a time, how the calculation is going on and how the weights is adjusted based on the equations that already we have derived. I will show you that. Okay, so let's see. So these are the set of steps. First of all, let's make it very clear. We will initialize with some weight matrix W that I have not told you till now, that I'm saying that value of W, but what will be the initial value of W? You see, you can keep initial value of W anything, because whatever the value of W is, based on that some error will come. Based on that error, we will have some, correction of the weights, and that weight will be automatically adjusted in the next iteration. So you can have any range of values for the weights. So it's just a blind initialize of the weight matrix W. Then we will feed the input data to the input of the input layer of the neuron. Through those, by weights, the summary value, summary unit basically will calculate the summary value. Then the activation function will be fired, and the output will be, some output will come, and then based on the target value, that output has to be calculated, how close it is. The error will be calculated. Based on the error, the adjustment of the weight will be done. So this is the whole scenario. Now feeding the input to the input layer of the neural network and flowing it towards output is called forward propagation. So what you can see here, forward propagation is means that from input layer towards output, the input features are propagated. Okay. Then naturally, you see, as given in the third step, calculate the actual response and calculate the error. And then we will simply calculate the delta Wj, that is the correction of the weight. And we will correct accordingly. We will adjust the weight matrix. I'm saying weight matrix. Why? Because later phase of the learning, you will see that we will represent these weights. I have various weights like W11, W12, W21, W22, W31, W32. It's not single variables. It's better to put in a matrix form so that we can do a easy matrix calculation. Anyway, when we will practically try to write the code, then maybe it will be much more clear to you in future. Anyway, so then the next iteration will be adjusted and go back to the step 1. I'm sorry, it should not be step 1, because at initialize cannot be done more than 1. It should be go to step 2. So I will feed the next pattern and forward it to the output, and then again, actual, based on the actual response, error will be calculated, weight will be adjusted, and so on and so forth. So this is the whole idea of teaching a model. Now let's come back to the example again, and let's see what's happening if I follow this set of steps. So you'll start with this. You see, so I'm taking the first pattern. I have this class level in my hand. This class level will be useful once I will get the output, the predicted output. Okay. Since the class level is a binary classification it's a binary classification problem, so I'm considering class level as either +1 or -1. And since I have presented the class level as plus or minus, that's why I have used signum function here, because signum function gives output of the neural network as only +1 or -1, so it will be easier to interpret. Maybe if you consider some another class levels, based on that the activation function may vary. right? Anyway, let's start with this particular pattern and assume the learning rate is 0.01, which is eta. Okay, so what we will put, we will put 121, 16.8. These two are features. Remember, this is my bias. It has to be there, whose value is always 1. And the value of W that you can see, W11 as minus 10, 10, 10. This is an arbitrary value. You can put even 100 as well. No issue. It will be adjusted automatically. So it will be calculated, and then some function will be fired. I mean, the signum function will be fired, and I'll get output, and based on that we'll have a weight adjustment. How it will done? Let's go to the equation level understanding. So let's see what is U. U means J1 to 3. J means here the neurons. I'm considering this is also a neuron whose value is always 1. Okay. So J1 to 3, Wi1 xi, like 121 multiplied by minus 10 plus 16.8 multiplied by 10 plus 1 multiplied by 10. As a result, you will get minus 1032. Maybe. If you calculate, you will get that minus 1032. Now, according to signum function, since the input of the signum function will be minus, that means something less than 0, naturally output of the signum function will be minus 1. That's the nature of signum function. You can easily understand that. So it is predicting output is minus 1. Now let's see what should be my error. Definitely it's not correct. Whatever, correct or wrong, that's later issue, but I have to find the error first to adjust the weights. So this is the weight adjustment calculations happening here. What is W11? Delta W11 is nothing but eta multiplied by t minus y multiplied by x1. Already you have seen this equation. So just put this. T means target, which is plus 1. Y means the output, that is minus 1. So plus 1 minus minus 1, that means basically 2. So 0.01 multiplied by 2 multiplied by x1, that is 121. If you do this, you will see the value of delta W11 will become 2.42. Similarly, if you calculate the other two delta W, you will get these three values. Okay. Now, naturally, if you consider some other initial value of W, this value will vary, obviously. But I am not saying that this is the best value of the W even in the first run. Maybe you need to go for multiple iterations, and automatically this W will be adjusted. Okay. So you have got some delta W's. Once you get this delta W, naturally you can add this delta W with the present W to get the new W that we can have. So present, for example, if I consider W11 part, W11 initially was minus 1. Delta W I got as 2.42. So minus 10 plus 2.42, it's minus 7.58. It's a bit decreased. Similarly for, I'm sorry, by mistake it is written W11 for all, but obviously I hope you can understand. It should not be W1, it should be W21. It should be W31. Similarly for this one as well. For this one as well. Okay. And accordingly they are adjusted, you see. Some weights are increasing, some weights are decreasing. So it will depend upon the value that I have given here, initial value of the W, as well as the output and all, everything depends. Okay. So once we get the new value of W, what will happen? These W's will be, replaced. These values will be replaced by the new value, and I will get these new values in the W. Next time, when we will pass this pattern, we will fit this pattern in the input of the neural network. Now the calculation will be again similarly, but here W changes. Once W changes, naturally all this calculation will change, right? So delta W11 now becomes 2.2228. Previously it was 2.42. Now it becomes 2.28. So naturally it will be adjusted to minus 7.58 plus 2.28, so minus 5.30. And similar calculation will happen for the other W's. So I hope again also you can, since I've just copied some part of this code, so that's why it remains same. Anyway, I hope you can understand. It should be W21 and it should be W31. So in this way, we can adjust this value of W. Once we will go through, it's actually the only second iteration, you can say. Then third iteration left, fourth left, and maybe after going through these four cases, we can repeat from one again. That let's see how good the teaching, the learning happened, to check. So what actually we have done till now, we are passing first pattern in one first iteration, then in next iteration next pattern, then in next iteration third pattern, then in fourth iteration fourth pattern. After fourth iteration, what I can do, I can start passing the first pattern again, then second again, then third again, then fourth again. So the order of feeding the inputs to the neural network is 1 2 3 4, then again 1 2 3 4. So this 1 2 3 4 you can consider as a set, right? So if you consider the whole thing is a data set, whole data set that I have, so what basically you are doing, you are passing the data set again and again. This again and again passing same data set, technically in language of machine learning we call epoch. And within a particular epoch, we are passing the patterns one by one. Those are iterations. So you can say it's a nested loop with respect to a programming point of view. In the outer loop, we have epoch. In the inner loop, we have iteration. We start with epoch 1. This is iteration 1. Then iteration 2. Then iteration 3. Then iteration 4. First epoch completed. Next epoch, we will start again. Iteration 1, iteration 2, iteration 3, iteration 4. Second epoch completed. Then again, third epoch starts with iteration 1, 2, 3, 4. So on and so forth. So this concept of epoch will be highly useful in future when we will start writing the code for complex problems. It's like you can assume as an analogy, like you are learning or trying to learn a particular chapter of your book. So what you are doing, you go through the each and every lines of the chapter once, and maybe then you realize that it's not fully learned properly, so you start from the first line of the chapter again. So you are reading the chapters more than once. So this is nothing but epoch. And within the chapter, when you are learning from first to last, all the lines, the texts, that is the iteration. I hope the concept of epoch and iteration is very clear to you now. So this is by which I have not given I have not extended the mathematical calculations for the other for the other patterns here in this data set, because I hope if this first two pattern calculation is clear to you, then you can easily go for the other two, and even you can repeat by epoch as well, right? And once in this way, by repetitive epochs and iterations, once the model will get trained properly, then we can utilize that model to understand what should be the class for the unknown fruit that we had in our problem. Now, definitely a question will come, how you will understand the model is good, learned properly well. How to test this? So this question definitely will arise. We will go through, we will actually address this question, but it is not very much required right now. Just for time being, you understand that definitely there is some way. We will see that soon. So let's move forward with similar type of problems in a very, as a overview. Like if I have some more example, say for example, let's take a very simple example: implementing AND function. This is also a function. These two are features, A and B, and F is the output. Right? We have four patterns. Is it possible to create a singular perceptron for learning this particular data set? It is a data set also, right? Small data set, but data set. Is it possible to learn? If you put the zeros and ones for these different input features in a plot, if you plot that, you will see it looks something like this. So these reds are showing zeros, for which I'm getting zeros for A's and B's. This side A and this side is B maybe, and the violet one is for 1. Now you can see, you can easily draw a straight line. It will linearly separate the two, two patterns. One pattern of Y, one for 0. Fine. Is it possible for OR function? It's OR also almost same. That's like 0, it's 1. So, it's something like this, just an opposite one. So again, you can simply draw a straight line. You can actually derive a straight line by the concept of singular perceptron. Fine, you can draw this. But what about this ZOR? This ZOR has a very complex and interesting, representation in the 2D plot. It looks something like this. You see, the violets are seen here and here, and grades are here and here. Now, if I ask you to create a linear separable line, you see it's not possible. Anyhow, wherever you draw, there will be at least one misclassification present. So that means ZOR is basically a non-linear function, and this is not linearly separable. And here the single layer perceptron fail. So from this particular examples, what we have understood, that single layer perceptron cannot classify nonlinear separable patterns that we have observed. For example, ZOR operation. So we must go for some solution, right? And the solution will start with a concept that is Cover's theorem. So we will understand the Cover's theorem first, and then we will try to realize how this Cover's theorem is actually modifying the single layer perceptron so that it is solving the problem of nonlinear separable patterns. So let's go to the Cover's theorem.